Okay, welcome back to the second part of the first programming session for the Foundations of Machine Learning lecture. In this part, we will be looking at an introduction to Numpy, which is the numerical computation library or core library for scientific computing in Python. And it's also what we will use throughout the semester to implement our machine learning algorithms in an efficient way. The basic units of Numpy are arrays, so multidimensional data objects which kind of relate to the mathematical concepts of matrices. And you can formulate most of the machine learning algorithms you get to know in this lecture in terms of matrices. So I will first iterate over some of the basic concepts for working with Numpy arrays. I'm working with Numpy 1.23.2 here. If you have a different version, that's mostly fine, but if something doesn't work, try upgrading to this version first and see if it works again. In most cases, it will fix it. Also, since this is the first week, this is still a very non-interactive lab version, so there is little you are supposed to program yourself. Mainly, we want to use these first series of exercises to establish like a common ground for everyone, so we can actually start implementing things in the next set of exercises for session 2 of the lab. So a Numpy array is a grid of values, and all of these values have to have the same data type. We can work with Numpy arrays in the same way we might work with lists in Python. So we can do indexing, we can do slicing, but we can also do much more. And one of the important differences between Numpy lists and Python lists and Numpy arrays is that we can use multiple indices. We can also have other Numpy functions on top of it. So an array is really the basic type that we deal with when computing things in Numpy. To create an array, one of the simplest ways is to just use a Python list as basis and cast it into a Numpy array. And as we can see here, this is now an array object. As with Python lists, of course, the bracket notation for accessing a single element still works. So we set the 0 element, so the first element in our Numpy array, to 5. Then if we compare, before it was 1. Now if we print it again, it is actually 5. To get multidimensional data in Python lists, you would need to nest them into each other. So we have 2 lists of length 3 inside one larger list. And this would correspond to a Numpy array with 2 dimensions. So we have 3 columns in 2 rows. It corresponds to the 2 lists. So row is always our first dimension, and then 3 columns, and columns are always our second dimension. Numpy arrays can have an arbitrary number of dimensions. I think the most people encounter in this course, however, are 3 dimensions. So there would be a depth dimension to this as well. For now, we will stick to 2-dimensional lists. You can infer different kinds of information about an array as soon as you created it. For example, we can get the shape, which is the number of rows and the number of columns. In the 2-dimensional case, in the n-dimensional case, each of these would correspond to an axis or one of the dimensions, and will tell you how many values there are along this axis. Along the 0 axis, which corresponds to rows in our example, we have 2 values, and along the column axis, we have 3 values. You can also get the data type because Numpy arrays are typed, and if you create a Numpy array from a list, it will automatically infer the type for you. So in this case, we have an integer array. I can also change this to 1.0, and then we have a float array because it recognizes that this in Python is a float value. You can also make this explicit during creation by appending a dtype equals argument. And if we type in float 64 here, you can see our NumPy array is now also in float 64, even though the values we supplied are in integer form. I can achieve the same behavior by casting something. So the s-type function returns a view of the array in the specified data type. So if I have something that's created as an integer object, but I want to convert it into floats, I can just use s-type to do that. The size of an array corresponds to the total number of values and will usually correspond to the product of the shape. Now, not in all cases I have a Python list to base my array upon, and for this case NumPy actually provides many functions. The first one is zeros, and I specify the shape of my output array. So in this case I would like to have a 2x2 matrix of zeros, and as we can see NumPy supplies me with that. I have also the similar ones, which gives me the same thing. I supply a shape and NumPy fills this shape with 1 values. In this case, I created a 3x2 matrix, so 3 rows, 2 columns. And in case I want any arbitrary value, I can also use numpy.full, which takes as a second argument, besides the shape, the value I want to fill it in with. And here I also have free choice over the data type. Also note that each of these functions has different optional keywords. For example, the data type, I can type in int32. And now I have int32, and it will tell me that it's a special data type. One important difference here is that Python internally, in the original form, uses only 64-bit numbers. But NumPy, since NumPy is backed by C arrays in memory, we can actually specify the exact number of bits. So we also have int8. And this, or int16, or int32, and so on. Same with floats. This is important because sometimes you have a large number of values that are close to not fitting on your RAM anymore. So you can scale down the resolution, so to speak, the resolution of the numbers, and fit more data into your RAM. However, you reduce the precision. So only do this if you're sure that the numbers you want to save there actually fit inside the number of bits you provide, or that you're fine with using this resolution loss. There are a couple more specialized functions to create specialized array types. One is I, which is short for identity as a shorthand. An identity matrix is just like a square matrix where the values along the diagonal are 1 and everything else is 0, and I just supply the side length of this square matrix. I also can create random arrays. So I have the numpy.random submodule, and this has many different functions to create arrays. I can draw from different probability distributions. I can draw different data types. In this case, I just have the basic random function, which returns the specified shape drawn from a uniform distribution between 0 and 1. The 1 is non-inclusive. Okay, now that we have arrays, what can we do with them? In the most basic form, we can do arithmetic. And most operations in NumPy are automatically vectorized. Vectorized means that we take a function and apply it to each element in parallel. And this makes it much, much faster to work on data. So all arithmetic operations are parallelized by default, as we can see here. Adding +5 to the array actually adds 5 to every single element in our array. So if you compare the numbers up here, the difference is just 5 for every single one of them. And this computation is done in parallel. So we don't need the usual construct in Python for lists where we would loop over the list, add 5 to each element explicitly, and then have our new list. Here we can just do it in parallel in one line of code without any extra overhead. Keep in mind, though, that since most of these operations are vectorized, you need to make sure that this is actually what you want. For example, if you only want to add 5 to the first element, you would need to slice it by appending a 0 here, and then you get a +5 on the first element. You can also use 2 arrays as input to an arithmetic operation. If we have 2 random arrays here, we can, for example, add these random arrays. If you remember, this random function gives uniform between 0 and 1. We can see there are values that exceed the 1, so we actually successfully added these two. We can also multiply them, we can divide them, and so on. But we can also compare them. So this would be an element-wise greater than comparison. And if the first array is greater than the second array, or the value in the first array is greater than the value in the second array, this evaluates to true or to false in the other case. One caveat here is that for each of these operations, the two arrays need to be of the same shape, because otherwise you can't really compare element by element or add element by element. To get a single value out of an array, as I already hinted at, we can use slicing. In the one-dimensional array cases works exactly as with Python arrays. For example, to get the fourth value at the index 3, we just put the square bracket notation that you know from standard Python here. And as we can see, this is indeed the fourth value, at index 3. Since we have often arrays with multiple dimensions, this notation is extended. So in the normal standard Python case, you would do a nested indexing to get to the nested values. So if you want to get this value, for example, you would first index the second list. So this would be index 1, and then you want the first value. So this would be this. However, in Numpy, you can just do it comma separated inside the same bracket. And the reason for that is just that it's easier to write, especially if you deal with slicing. Slicing is an operation where you don't want a single value, but rather you want a continuous range of values. And in standard Python, we also use the colon character, but in Numpy, we can also do it over multiple dimensions. So I want every value of the first dimension. We don't supply any values here, so the colon just evaluates to everything. And we want the first and the second. Again, slicing is not inclusive of the end, so this is just 1 and 2. So I have the second column and the third column. This is also 0 indexed, so second and third. And I want every row, and this corresponds to these 6 values down here. One thing to keep in mind, if I wouldn't put this copy here, Numpy returns a view. And a view means that if I change something in this new variable, for example, I set 0, 0, so this 2 right here, to 77, my underlying array would get modified. So if we have a look at the underlying array, which is the one from up here, we see that this 2 is now a 77. However, if we just execute all of this again, and this time we invoke .copy on it, run this again, this copy actually creates a new memory for us. And if we modify this, the original memory stays untouched, and we still have the 2 here. So this is a source for many, many programming bugs. So keep in mind that if you don't explicitly copy something in Numpy, it will just keep working on the same memory structure. And this makes it very efficient because you don't reuse memory or copy memory all over the place. You just work on one single location. You normally work on pointers to the data, not the data itself. And if you want something to be duplicated, you need to explicitly copy it. We can also use Boolean indexing, which means that we just supply a Boolean matrix of the same size, the same shape of our original array. And then we get every value back where this new masking Boolean array is true, and we don't get the values where this is. So if you look here, we get the first, the third element, and so on. Okay, reshaping and transposition. We talked about slicing and how you can get different views onto data, but these are still bound to the same dimensionality. And if you want something in a different dimension, for example, you want to reduce a 3-dimensional array to a 2-dimensional array, you would need to do a reshaping or a transpose. So in this example, we construct ourselves an array with the shape, or a one-dimensional array with 9 values, so from 0 to 8. And we can now reshape this into a 3x3 matrix. And this works because this is the same number of values, just in a different order or different arrangement. However, if I would try to reshape this into a 4-2 matrix, this will not work because we have only 8 values accounted for here, but we have an array of size 9 as input, so we can't reshape it. So reshape, you need to make sure that the result shape and the input shape have the same size. So the number of values stays the same around both views. So for example, I could do this, which nests one more dimension in here. I can also do this, which nests it in even more dimensions here, and I can just keep doing this. As long as the total product of a shape, so the number of values stays the same, I can do whatever I want to here. Transposing works a bit differently. Transposing is to swap different axes of an array. So if I have my values row-wise and I want them column-wise, I can just transpose and switch the first and the 0 dimension. So for example, I have an array here, 1, 2, 3, and this is now row-wise data. So I have one row with 3 columns. I can transpose the 2 dimensions. So I swap the first and the 0 dimension, and I now get something that has 1 row but 3 columns. No, other way around. 1 column but 3 rows, sorry. Also, if I only want to ever switch the first 2 dimensions, I can use this capital T shorthand. If I want to have different dimensions deeper into the data, so I want to switch the first and the, I don't know, 5th dimension or something, then I would need to use the explicit transpose function. Okay, universal functions. Universal functions is nearly everything in Python and Numpy that takes a Numpy array as an input to a function and either puts out another Numpy array or a singular value. And these universal functions are vectorized by default, so they are very, very fast. So whenever you deal with something that is a Numpy array, have a look if there's a corresponding function available inside Numpy to achieve what you want to do, because usually it will be much, much faster. Numpy under the hood calls C and does calculations using the native C libraries, so it's much, much faster than using default Python. There are more than 60 functions defined here, and I put the link to the documentation in the slides where you can refer to them. And we will only have a look at a couple of them as a subset here to get you to understand how they work. The most commonly used one is sum. So this gives me the sum of an array. This would be the total sum, but you can also supply an axis and it would sum along this axis. So for example, if I supply the axis 0, which is the rows, it would sum the rows in each column. And the first column would have the sum 3, the second column would have the sum 5, and the third column would have the sum 7. There are also different other mathematical operations, such as logarithm. There's not only log, there's also log 10, log 2, and all the different bases. You can also do exponents here. Note that this actually throws a warning because you have a divide by 0 here. And this is also another difference to standard Python. In standard Python, this would throw an exception. In Numpy, this will throw a warning and insert a negative infinity. And so you would either have to deal with this. Most Numpy functions can deal with minus and plus infinity by default, or missing values are also possible. So just be wary of that Numpy may ignore these exceptions and rather throw a warning at you. There are also universal functions that not take a single array but 2 arrays and somehow manipulate them. I have 2 random arrays here between 1 and 2, so 0 and 1, and 5 values each. And np.maximum finds the maximum of these 2 arrays at each position. So at the first position, it looks at both arrays and sees, okay, the maximum is 1. And I can do that with infinitely many arrays and nest them. And in this case, because 1 occurs at each place in each array at least once, we have just a maximum array filled with ones. Don't confuse this maximum with np.max. Let me quickly illustrate this here, because np.max is actually the singular form to avoid confusion. So this would give me the value. Wait, I have to execute this first. Okay, this will give me the value at this index, the maximum of this array, sorry. But maximum as like the whole name will compare the two arrays and give me the maximum at each step. And now that we recalculated our random numbers, we can see that there's a 0 here at both positions, so we get also a 0 now. We can also do logical operators, so logical AND, logical OR, logical XOR, and stuff like this, which will just give you a Boolean vector back on the position-wise comparison. So we have 0 and 1, which is false. We have 1 and 1, which is true, and so on. Numpy also features a way of doing conditional logic without relying on if and else. Again, using built-in Python structures is slow. So if I were to write an if-else block in any circumstance that I might need it, I would have very slow code. We can speed this up by using the built-in numpy.aware. And aware statement has the form condition, then whatever it should insert if the condition evaluates to true, and the data it should insert if the condition evaluates to false. So in this case, let me illustrate this. We take a range of 5 values, of 6 values as input, so from 0 to 5. And our condition is if this is actually larger than 2. So we have a Boolean array with 6 values, false, 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 true, true, true. And now if this array evaluates to false, which is our condition, we want to insert a 0. And if it evaluates to true, in the last 3 cases of our condition, we want to insert a 10. So if we run this, we get a value of 10, 10, 10. So the data if this evaluates to false, and 0, 0, 0, which is the data if this evaluates to true. This can be extended by taking data from equally shaped arrays. So if our array has the same shape as our input data, so we have 2 arrays up here that are 3 by 3 with 9 values. Let me print these so you can have a look at them. So we have 0 to 8 in the first and 10 to 18 in the second. And we now have a Boolean mask, which is just also a randomly generated mask, but it has true and false values. So here, if the mask evaluates to false, we will take the data from the first. We will take, if the mask evaluates to true, we will take the data from the first array. And if the mask evaluates to false, we will take the data from the second array. So here we can see for example, in the upper left corner, we have the false. So we have the 10, which is the upper left value here. We have the 2 here because this is true, and the 2 value is up here. So this is also, again, just an element-wise vectorization of the conditional logic if-else statement. Numpy also features statistical methods, which come in very handy for many machine learning tasks. So we can very quickly calculate the mean or the variance of an array. We have lots of other different statistical functions available, but just these to illustrate what Numpy is capable of. If we randomly generate 10,000 numbers, they are about 0.5. Again, this is pseudo-random and also a rather small sample, so this will not exactly be. But if I increase this, this should be 0. This will get more and more precise to the actual true mean of randomly, uniformly generated data between 0 and 1. Quantifiers would be the next topic. And quantifiers are very important because an array has no single truth value. As we have seen before, we can do element-wise Boolean comparisons. So we can check if this numpy a range of 10 values, so 0 to 9 is bigger than 5. And this gives me the same shape but as Boolean, so we get 10 different Boolean values. But what if we want only a single one for the whole array to maybe compare things? This is where quantifiers come in, and they correspond one-to-one to the quantifiers you might know from either discrete structures or logics. So the all quantifier and the exists quantifier. And the all quantifier evaluates to true if every single value in the array you give to it is also true. So in this case, it would be false. And the any or the exists quantifier evaluates to true if there's at least one true statement in this array. So in our case, this would evaluate to true. And the last topic I'm going to talk about today is sorting. Similar to Python lists, NumPy arrays can be either sorted in place or you can return a sorted view. So if we just have an array of random numbers, we can call sort on it, and this will return a sorted view. However, if you view the original data, it is still in its unsorted form. If we instead call the array.sort method, the underlying array will actually get modified. So if we later print it, it is still in sorted form. This corresponds to the built-in Python statements that if I have a list and call .sort, the list will get sorted in place, but if I call sorted on a list, it will actually only return a sorted view or return a copy of the sorted values in standard NumPy. In standard Python, in NumPy, it will be a view. And I can also sort along a specified axis. So if I have this 3x3 grid of random numbers, and I say I want to sort along axis 1, this will sort each row on its own. If I say axis equals 0, this will sort each column on its own. And of course, I can also say it should be reversed and things like that. So this concludes our short overview on NumPy. These are the basic features that we expect you to sort of be familiar with or not get confused if you see them in code in the next coming weeks. So make sure to go over this notebook once again on your own time and see if you understand all the concepts at play here. And next exercise, we will start with actually implementing things. And this first implementation in the next exercise will be evaluation metrics. So I'm looking forward to seeing you back again in the next version.